So I'm going to talk about some selected results from local helioseismology. And before I get started, I wanted to say a little bit about the thought process here. This really is selected results. We learned a lot of things from local helioseismology, and here I'm picking some of them. I'm not at all attempting to do a historical review here, and I'm certainly not trying to do a comprehensive review. It's really just some particular topics that I think are interesting. So with that, we'll talk about meridional circulation a little bit and torsional oscillations. I'll have one slide on far side imaging because I think it's cool. And then we'll go into a little more detail on some recent results about Rossby modes and the amplitude of convection. So let's start with meridional circulation. It's been known for a long time that at the surface of the sun, there's an axisymmetric flow in the sense of the equator to the poles. And this flow has to close somehow. I mean, you have to conserve mass. There must be a return flow somewhere. And maybe there's more than one cell in depth. That could be. And one reason this flow is interesting is that it's important for flux transport dynamos. In this class of dynamo models, the time scale of the cycle is set by the time scale of this circulation. Another reason I think the meridional flow is interesting is that it's important for understanding the effect of rotation on convection. And that's because you want to understand how the meridional circulation is maintained. And so it brings the obvious question, okay, what does the meridional circulation look like beneath the surface? And this is something that can be addressed with local helioseismology. So I'm going to focus here mostly on one early result. This is a paper from Peter Giles in '97. And he used time-distance helioseismology to estimate the meridional flow beneath the surface. And in this work, he was not trying to use a bunch of data and make measurements that go all the way to the base of the convection zone, but he was using somewhat less data than what people use now. But he was looking relatively near the surface, so in the top 20 megameters beneath the surface. There have been a lot of papers since, but one reason I think that this Giles paper is interesting is that it really uses a lot of the common elements that showed up later. And I also like it because it connects clearly to some aspects of time-distance helioseismology that we talked about in the last lecture. And again, I'm absolutely not trying to present a comprehensive review of meridional circulation here. This diagram in the bottom left, you have to squint a little bit, but there's that little dark area in there. And if you zoom in, you see that what Peter was drawing there were ray paths. So you have these different ray paths, 1, 2, 3, 4, that penetrate to different depths in the sun. And he's using this symbol delta to tell you the distance between the endpoints of the ray path. And you see that the larger delta is, the deeper the ray path penetrates into the interior. And so what he did is he used MDI data and time-distance helioseismology to measure north-south travel times for these different ray paths. And remember that north-south travel times tell you about north-south flows. So that's the measurement. You take this little ray path diagram and you put it at some particular latitude, lambda, and you make a measurement of, say, the south going times minus the north going times, and you get something that's proportional to the meridional circulation. And here's one particular example. So the y-axis is this travel time shift and the x-axis is latitude. And he's averaged over a bunch of different travel distances, so a bunch of different deltas here. And you see, okay, there's something going on. When you're at the equator, this travel time shift is essentially zero. So this is telling you that the meridional circulation is small near the equator, which makes sense. And as you go higher in latitude, it gets stronger, and then something happens as you get up to 60 degrees. And on the other y-axis here, they've provided a calibration. So it's just, if you had a uniform flow, how would you interpret that travel time as a flow? And that's an interesting number. It tells you that this meridional circulation is getting up to 20 meters per second. So you already can read off a basic amplitude of the flow here. And the thing I like about this paper is it also shows a forward model. So instead of going straight to inversions, they asked a simpler question, which is just, okay, if I assume some particular model for the meridional flow, what do my travel times look like? And this is a really nice way to start interpreting local helioseismic measurements. They considered a couple of different models. There's a shallow model where you say, let's suppose that the flow is confined to the top 5 megameters and make a prediction for what the travel time shifts should look like as a function of distance. So again, the distance between the two endpoints of the ray path. And they also considered a deep model. And here you say, let's assume that the flow is uniform over the top 20 megameters. And you can make your forward models. So here the shallow model is the triangles, the deep model is the squares, and the observations are the filled circles. And you can understand the difference between the travel times coming from the deep model and the shallow model. Basically, these travel times fall off much more rapidly with the travel distance in the shallow model. More and more of the ray path is below the shallow layer, and the rays are much more vertical when they're coming through the shallow layer. So you get smaller travel times as you increase the travel distance. And that drop off is much less severe in the deep model. And so the nice thing here is that just by doing a couple of simple forward models, you already get an idea about what the data are telling you. It looks more like the meridional flow is a deep thing than a shallow thing. So that's already interesting. And of course, many, many other people have studied the meridional flow since then. I just wanted to show one other particular example because it connects to the torsional oscillations results I'm going to show in a minute. And that is the meridional circulation is not just a fixed thing that's independent of time, but it changes with the activity cycle. And here's a figure showing that. So we're looking at a diagram that shows time and latitude, and the colors in the background are U theta. So this red color means a poleward flow, and a blue in the northern hemisphere, and blue color means a poleward flow in the southern hemisphere. And these black contours are telling you about activity. And what you see is that the patterns in the meridional circulation approximately follow the patterns in the activity. Here you see this equatorward drift of activity as the cycle progresses, and you see that pattern clearly in the meridional circulation as well. A connected topic is the torsional oscillations. You can make the same kind of diagram and see that the east-west flows depend on the cycle as well. I wanted to connect this back a little bit to some things that we talked about in the global helioseismology lecture. We saw that the rotation rate in the sun depends on depth and latitude and time. And you can study this problem with local helioseismology as well. And it has some advantages in that you can study the northern and the southern hemispheres separately. And also you can study what are the actual local contributions to these azimuthally averaged flows. So to make a figure like this, like we saw here, we're averaging over longitude in the sun. These are just the azimuthally averaged components of the flow, but you can look at the flow maps before doing that averaging. And again, this is a big literature, and I'm not trying to do a comprehensive review here. And also, just as a little point of terminology, the time-dependent part of differential rotation, people call torsional oscillations. And here's an example of a figure. And much like the one we saw a minute ago for the meridional circulation, we have latitude and time. And the colors now, instead of telling us about the meridional circulation, they're telling us about the east-west velocity. So red here is prograde and blue is retrograde. And you can ask yourself, retrograde with respect to what? Well, with respect to some average. And the way that these plots look can depend somewhat on how you do construct those reference values. So that's something to keep an eye out when you're seeing figures like this. For example, here you look and you see red in this cycle and blue in that cycle. But this kind of thing is largely about what reference you subtract out. Okay, but the point I wanted to make here is again that you have these time-dependent zonal flows, and again they're following the latitudes of activity. The black spots here, sunspots. Again, as the active latitudes drift down to the equator, there's an associated pattern in the east-west flows that follows that drift. And a nice thing about local helioseismology is that you can go and you can look at that at a finer level of granularity. Here's one example. So now we're looking at a time period that just covers one rotation of the sun. You let the sun rotate underneath you and you can build up a map that covers a range in longitude. This one doesn't cover quite a full rotation, but it's a good part of a rotation. And these horizontal arrows are showing flows measured from F-mode time-distance seismology. And those black features in the background are active regions. And what you see is that there are converging flows towards active regions. And these things extend, some distance away, 10 degrees, depends how you want to define it, away from the active region. And the scale of these guys is over here. This is 100 meters per second. And just for reference, if you go back to this previous figure, the color scale is plus minus 6 meters per second. So these individual flows around active regions are quite a bit stronger. And then when you make these azimuthal averages to make a figure like the previous one, you get much smaller numbers. And this is one example. You can also go and look at that in a statistical sense. So instead of looking at flows around particular active regions, you can pile up a whole bunch of active regions and look for what they have in common. And this is a result from Doug Brown where he did that, where he looked at hundreds of active regions. And you make averages of these flow maps. You guys all understand these flow maps because we talked about them yesterday. So you're looking at horizontal flows near the surface after averaging over a bunch of active regions. And on the left, there's the case of small active regions, and on the right, big active regions. And the colors in the background, yesterday I showed horizontal divergence, but here they're just showing the magnetic field. So you have some blue in the leading polarity and these red colors in the trailing polarity, and the same in the other figure. And here you see these converging flows towards active regions. For the big ones, the situation is a little more complicated. There's a converging flow, but there are also some east-west flows. And there are some big diverging features here. I haven't looked at that sample of active regions in detail, but I suspect that this is coming from mote flows, from a few big sunspots. Okay. I wanted to show one slide about far-side imaging because it's neat. So here, what's happening, this is a ray path diagram. So imagine you're observing from down here. You're observing waves that you see on the front side of the sun. They bounce a couple of times. They bounce off some target point on the far side of the sun. And then they bounce again, and you see them again on the far side of the sun. And you can move this focal point around and make maps of something on the far surface of the sun. And that something is whatever it is that causes changes in wave travel times. So you make maps of wave travel times as a function of where you put that focal point. And here are some examples. The yellow parts of the map show you these travel times measured with far-side imaging. The dark regions are where the travel times are a little reduced. We're talking about 5-10 second size signals in the travel times. And the gray images are showing you magnetograms taken on the near side of the sun. So the part of the sun we can actually see directly. And we're looking at 3 different days here. So you see there's a big feature here in the far side map. 2 days later, you see an active region is starting to rotate onto the east limb of the sun, and that continues. So this far side imaging can actually detect active regions through their impact on the acoustic waves, even on the far side of the sun. And this is something that's interesting for space weather. It's interesting for understanding active regions, I think, also. And one thing that I'm looking forward to is that with the Phi instrument on Solar Orbiter. So Solar Orbiter was launched not long ago, and it will take magnetograms of the sun and also take helioseismology observations from way off the Sun-Earth line. And so it will be a way to calibrate these far side maps. We'll have simultaneous maps from far side imaging along with magnetograms. And so we can calibrate those. Okay, I wanted to say a little bit about Rossby modes also. Here's the one slide introduction to Rossby waves. The restoring force is the Coriolis force. The motions are essentially horizontal. They look like big swirls. So they have radial vorticity, but they don't have horizontal divergence. Here are some images on the right. You can see the north-south velocity, the east-west velocity, and the radial vorticity associated with an L equals M equals 5 Rossby wave. The dispersion relation of these guys is over here. It depends only on the rotation rate of the sun and on M. This is for the assumption of sectoral modes. They're hydrodynamic. They don't require a magnetic field. The phase velocity, you can see from here right away, the phase velocity is negative, so retrograde, but the group velocity is prograde. And you may have seen them before in the astrophysical literature. They get called R modes. And here's one example. So how can you find those in the observations? And here, this is a figure from a paper by Bjorn Leptjen from a few years ago. And we haven't talked about it yet. But in addition to helioseismology, another way to measure horizontal motions on the surface of the sun is to follow little convective features. There are these little guys called granules, and they get dragged around by the larger scale flows. And so just by following how those little convective features move, you can infer the larger scale flows. And you can make maps like this. So in each one of these figures, you're looking at a full rotation of the sun. So like I said earlier, you just let the sun rotate underneath you, and you can make a map that shows horizontal flows over the full range and longitude. And all of those little black arrows are telling you about horizontal flows measured from this feature tracking method. And the color scales in the background are telling you about the radial vorticity, so the swirliness of the flow. And with HMI, we have a whole lot of data, which is great. In this paper from Bjorn, he used 6 years of HMI observations. And for every rotation of the sun, he made one of these maps of horizontal flows and from those computed radial vorticity. And then you can put those maps through an analysis that's just like what I showed for global helioseismology. Imagine you just, instead of thinking about global helioseismology applied to Doppelgrams, think about global helioseismology applied to time series of maps of the radial vorticity. And this is what you get. So here we're looking at a power spectrum, just like we showed before for global modes. But now it's power spectra of radial vorticity. So the azimuthal order M is on the x-axis. The assumption here is that L equals M in this data analysis. And the y-axis is frequency. And black means high power and white means low power. And these black curves show the dispersion. This black curve here is the dispersion relation that you find in the textbook for Rossby waves. The panel below it shows the same thing, but the normalization is a little different. Here, in this bottom panel, the power is normalized differently at each M. It's normalized by the sum of the power. So you can see these lower M modes that you can't see here. And the issue is that overall the power increases with M, so you can't see much down here unless you renormalize a little. And if you look at a slice through one of these power spectra, this is for the L equals M equals 8 case. The data this gives you this black curve. It's astonishing how small the background is. This peak is way above the background. It's not just like a little detail, but this is the dominant thing that's happening in this range of frequency at this M. And you can fit that and you can measure all of the properties of the mode, just like for global helioseismology. You can measure the amplitude and the frequency and the line width. And from that, you infer that the lifetimes of these guys are months, and the amplitudes are meters per second per mode. And the lifetimes can be longer as you go to smaller M's. And it's not just that you can see Rossby waves in correlation tracking, but they've also been seen in ring diagrams. They've been seen using time-distance helioseismology, and they've been seen using mode coupling measurements. The figure on the left is an example of a measurement done using the ring diagram method applied to HMI observations. The scale is a little bit different. This shows a wider range in frequency. The Rossby waves are down here, and then you get a copy of the Rossby waves. This is, again, because we're not observing the whole sun all the time, so it's just a window function effect. On the right, there's an example of measurements made using time-distance helioseismology. In this paper, they looked at observations from MDI and HMI, so they could go all the way back to 1996. And again, you see the main Rossby wave ridge, and then you see copies due to the window function. You see some other interesting things. There's this excess power at low frequencies, which at least partly is due to active regions, I think. And then again, a copy of that due to the window function. And this has been studied in a lot of other papers in the last few years, and it's very clear that the people are agreeing on the detection of these features. So what are they? I wanted to say a little bit about the theory, even though it's not strictly a local helioseismology result, but it's important for understanding how to interpret the observations. I wanted to say a little bit about this paper from Damiani from last year. And she took the work of Provo and extended it a little bit and did this calculation of the quasi-toroidal modes, so the modes that are very close to just these horizontal twisting motions. And she did the calculation in a slowly rotating polytrope. The upper boundary condition here is a free surface. And what you find in this particular model is that the kinetic energy of the modes is not just a surface thing, but at least in this model, these modes are really filling up the convection zone. And if you look at the m=3 case, a lot of the energy is in the bottom half of the convection zone. Here I'm using convection zone very, very loosely. These are neutrally stable polytropes. There's no stably stratified convection and stably stratified radiative interior. I think it would be interesting to do that problem and see what happens. But the point I'm trying to make here is that, at least in this model, the Rossby waves are not a surface effect, but they look like something that's quite deep. And I think that makes them interesting. Another thing that you can squeeze out of the observations is you can determine the latitude dependence of the eigenfunctions, because you have measurements at different latitudes. Again, if you think back to those maps of radial vorticity. So you can extract the eigenfunctions, say, of the radial vorticity from the observations. And here are some examples. These shaded regions are estimates of the eigenfunctions in latitude. They're a little bit noisy, so these are binned in ranges of m, the azimuthal wave number, just to beat down the noise a little bit. And these lines are showing you just the sectoral spherical harmonics. So that's what you would get if you do the textbook problem of Rossby waves in a shallow water system on a uniformly rotating sphere, you find sectoral spherical harmonics. But it's not what happens on the sun. The eigenfunctions are somewhat more localized, and they even have a zero crossing. And in Laurent's paper from last year, he had a look at that in an equatorial beta plane model. So this beta plane model is just a little Cartesian patch around the equator where you let the Coriolis parameter vary linearly with latitude. And the interesting thing is that if you look at that equatorial beta plane model, but you include differential rotation, and that's shown in this panel in the middle, you can compute the eigenfunctions, and you see that they look, reminiscent of the observations. The blue curves, the solid blue curve is the real part of the eigenfunction in the model. The solid red curve is the observations. The dashed blue curve is the imaginary part. So these eigenfunctions are complex, and the blue dashed part shows the model for the imaginary part of the eigenfunction. And the dashed red curve is the observations. And this is for some particular choice of the viscosity in the model. So it's not a perfect match, but I don't think that's really the point. The point is that I think there's, it's a really interesting avenue to start comparing the observations with models and see what we can learn. And it is already interesting that the eigenfunctions in the model are complex. And I'll say more about that in a minute. So what that complex valued eigenfunction means is that the oscillations are out of phase at different latitudes. And one thing you find in this beta plane model is that the Rossby waves are transporting angular momentum in latitude. They're bringing angular momentum to the equator. And that's what this figure on the left is showing. It's showing you the acceleration due to transport as a function of latitude for some different things. The blue curve is the R modes, the Rossby modes in this beta plane model. And then there's also, these are some measurements from Hathaway. These are angular momentum transport by large scale flows. And this other curve is what you expect for supergranules. And the point here that I'm trying to make is just that in this paper, they argue that the Rossby waves are transporting angular momentum in latitude, and that this transport is non-negligible. And I think that's interesting and something that people should keep working on. Okay, one last topic, amplitude of convection. So the amplitude of solar convection at large spatial scales, I think it's fair to say, is not well understood. And this has been given the name the convective conundrum. And a related phenomena is that simulations of convection on the sun don't produce the right solar differential rotation without some tricks. For example, some people tried spinning their models somewhat too fast. And in turn, this has been taken as a indication that the convection in the simulations is too vigorous. And that's how it looks from the observations as well. There's an additional kind of complication here that some different helioseismic measurements don't agree either, but I'll say a little bit more about that in the next few slides. But let's have a look. So this is a map of east-west flows from one particular simulation. It was one of the cases from this Mark Misch paper. And the simulation code in this particular case was the ASH code. So you can take a map like this, and it's already interesting that you're seeing numbers like 1,000 meters per second, kilometer per second flows. And this is not quite at the surface of the simulation. The depth is maybe 0.96 of a solar radius, if I remember right. And so one way you can analyze this is just compute the power spectrum. So you take the spherical harmonic transform and plot. In this case, it's not a power, but it's the RMS velocity in a particular multiplet. But the idea is the same. You can imagine making a curve like that, this by just filtering the data to allow one particular L through, and then computing the RMS of the resulting map. So this is RMS velocity as a function of angular degree. And you can think about that as a function of spatial scale. So the largest spatial scales on the left and the smallest spatial scales on the right. And you see a peak in that RMS velocity per multiplet at about L of 20. You can measure the amplitude of convection from helioseismology. And I wanted to show this one particular example. So this is from the Hanasoge et al. Paper. And what they did is they measured east-west travel times. Remember, those are things that are proportional to east-west flows. And then they use some calibration curve that comes out of theory. So it basically says, if you had flow with a particular shape and depth, how would you convert these travel times to flows? And then there's another correction to take care of a signal to noise ratio, because some of what you measure in this map is noise and some of it is coming from flows. And you try to isolate the part that's coming from flows. And you can plot that thing on the same figure. So again, you take these time distance travel times, you calibrate them to east-west velocities, and then you do the same spherical harmonic transform, and you look at the RMS velocity per multiplet. This figure might look a little different than ones you've seen before, and it's just about fixing a few little bugs. This curve now is showing M summed power rather than M averaged power. But that's, at this level of detail, it's not so important. The point is that you get some estimate from time distance helioseismology. And you can think about this as an upper limit. And it's interesting to also plot the curve that you get by doing granulation tracking, like I talked about earlier. And this is what people are talking about as the convective conundrum. The velocities in the simulation are an order of magnitude higher than the velocities in the observations. Then, to make things a little more complicated, Greer and his colleagues in 2015 had a look at this problem from the point of view of ring diagrams. And remember before, when we talked about ring diagrams, we talked about making one measurement per ring tile. And the end result of that is that you don't have a lot of spatial resolution. If you put your tiles one next to the other, you end up with a spatial resolution that's like the tile size. And they proposed an interesting way around that. What they said was, aha, well, no one said we have to put our tiles directly next to each other, or another thing that's been done in the past is overlap the tiles by 50%. But they said, no, what we're going to do is make very, very, very overlapped tiles. So you get measurements on a very dense grid, even though the tiles are highly overlapped, and then stick the whole thing in a 3D inversion to infer the flow field. And the resolution that you get on that is something like the resolution of your spacing between the tiles, rather than a resolution that is like the tile size. So that's an interesting idea. And if you plot the curve that they get, you get this blue curve. So, tough. It doesn't agree with the time distance at the low L end. Yeah, there have been some newer measurements that show, from ring diagrams, that show a curve that looks closer to the time distance measurement. But there's still some things to sort out here, obviously. Yeah, so for the outlook, we've seen that the zonal and meridional flows change with the solar cycle, and that these changes are connected to activity. We've seen that there are flows associated with active regions, and it's an interesting question, and it's being discussed. To what extent do these flows associated with active regions explain the cycle variations of the zonal and meridional flows? I think that's a nice question. Rossby waves have been seen on the sun. There's been a lot of recent work on that topic, but we're just getting started. I talked a little bit about the convective conundrum. Convection on the sun is weaker than in the simulations, and it's not totally clear yet what's going on. I wanted to say just 2 words here about what's next for local helioseismology. Currently, there are a lot of choices that get made in the process of data reduction. And those choices are usually made on the basis of intuition, which is often, a very good thing. At the same time, I think there's room for optimization still. We still, as a community, need to keep going on characterizing convection. There are puzzles still. And Rossby waves are new and exciting, and work on that will continue. And one particular thing that I'm looking forward to are the observations from Phi on Solar Orbiter to study the high latitude regions on the sun. And also that will give us observations from off the Sun-Earth line. Yeah, that's what I wanted to show today. Thanks, everyone.